everyone, I'm Jia from Fuxi Lab, NetEase. The video you just watched is a demonstration of Dance Creator, which allows people to animate characters dancing using AI. Dance Creator is a system that automatically generates high-quality, production-ready dance motions based on music with arbitrary length. Today, we're very excited to share it with you. This work was done in Fuxi Lab NetEase games with joint efforts from Intel and is powered by oneAPI. This is our team in Fuxi Lab. We are a group of researchers and engineers dedicated to the transformation of game production and experiences through AI technologies. This is our agenda for the talk. First, we'll give a little bit background about why we want to build such a system. Then we will dive into the details of our system that generates production-ready dance motions from music. Finally, Yaru from Intel will talk about how Intel technologies help us to improve the performance of our system. Synthesizing animation through algorithms has drawn great attention in the industry recently, especially after some data-driven methods such as motion matching showed prominence in real production. Our focus is on dance animation, which also has huge demands not only from traditional games, but also from increasing numbers of new virtual experiences in VR and AR. This video shows how we created the traditional Chinese dances in our latest MMO, Justice. With the help of motion capture, we can produce high-quality dance motions. However, hiring professional actors to record every piece of dance is expensive, let alone the huge investment in these motion capture devices. Moreover, cleaning up animation data can be very cumbersome. So in practice, not every sound gets its chance to record its dance motion. We have other alternatives to make dance animations. Typically, dance motion is related to sound structures. This picture shows the structure of a sound. We can see a sound can be divided into sections like intro, verse, choirs, bridge, etc. If we make enough clips designed for each section as building blocks, then we can construct a longer animation for a given sound. This alternative way of making dance animation might reduce the cost by sacrificing some motion quality, but even so, it requires a lot of human labor during the whole process. So, our goal is to design a system that can automatically generate dance motions with minimal human intervention. The most obvious solution to this problem might be using a neural network, either a CNN or RNN, to learn a mapping between music feature sequences and dance motion sequence. So when we input a piece of sound, the network gives us the corresponding 3D animation. However, the quality of this end-to-end solution is not stable due to the lack of paired training data between music and 3D motion. Since we don't have enough paired data between 3D motion and music, we start to look for other alternatives. We found there are a lot of choreography videos publicly available on internet. With the help of human body key point detection algorithms, we can transform these videos into paired data between music and 2D motions. With these choreography videos, we now have enough data to learn a mapping between music and 2D motion. If we can somehow set up a relationship between 2D and 3D motion, then we can indirectly generate 3D motion from input music. The bridge we set up between 2D and 3D motion is called cross-modality motion feature, which reflects the energy and impulse that is shared between 2D and 3D motions. This graph shows the overall idea of our system. The input music is first translated into cross-modality motion features. Then we match these features to pre-recorded 3D motion data to get our final dance animation. However, there is still a problem. The number of pre-recorded 3D animation clips is very limited compared to the input music. So we decided to cut these 3D motions into smaller pieces to increase the diversity of output and perform what we call phase-based matching to make sure the generated motion is coherent and matches the input features. This is the overview of our system. On the left side are our data sources. First, we train the audio motion interpreter network that output cross-modality motion features using the video data and its audio tracks. We also extract similar features for 3D animation in the database. We perform a phase-based matching to find a sequence of clips that best matches cross-modality motion features predicted by the interpreter network. Before getting the final output, we work the dance motions as a post-processing to enhance its rhythms. Now let's talk about the audio interpreter network. To train such an interpreter network, we collected 200 video clips with 3 to 6 minutes each. Most of these videos are from professional choreography studios that covers dance styles like K-pop, urban, Chinese traditional, etc. The tempo of the sounds varies from 120 to 200 beats per minute. Then the features shown in the graph were extracted from these videos we collected. They include music features such as mouse spectrogram and cross-modality motion features, including impulse feature and energy features. Here, the impulse feature reflects the beats within motion, including when a motion beat happens and its beat strength. The energy feature relates to the joint's rotation speed and was extracted from several joint sets, together with the motion impulse features. After we got music and cross-modality motion features, now we can train the interpreter network. However, they are in two different domains. Therefore, we introduced the CNN autoencoder to map motion features into a latent domain. Moreover, to solve the gradient vanishing problems, we use independently recurrent neural network, which is a model optimized for longer dependency modeling tasks. Overall, this is the so-called CNN-IND-RNN interpreter network structure. Now, let's talk about the phase-based matching. As we mentioned before, we need to cut the 3D motions into smaller pieces in order to increase the diversity in output motion. What we did is to cut them when motion beats happen. But how do we make sure the dance motions are reconstructed in a meaningful and coherent way? Besides the position and speed of joints should be similar enough at the transition between clips, the extra constraint we added is called phase. The concept of phase comes from the observation that most modern dances consonate, which means that dance movements can be grouped into sections of 8 music bits and form a repetitive pattern. The phase of a small motion clips is the relative position within the cycle it lies in. As an example, here we show a 16 beats long motion feature cycle. Let's say we're trying to find candidate clips starting at phase 0. In other words, clips starting at the beginning of motion cycle. Then the phase of candidate clips must be 0 as well. The phase of motion clips must be the same as the phase of underlying motion feature cycle. This rule makes sure that after motion reconstruction, the small building block clips stay at the same relative position to a 16-bit cycle, thus preventing the generated motion from breaking the repetitive pattern. Even though phase-based matching could generate motions that should overall match the input music, there can still be mismatches between the motion rhythm and music bits. Animation warping guarantees that both motion and music bits happens at the same time. To satisfy such constraint, we adjusted the playback speed of motion sequence. On the top of the graph is the motion playback speed before animation warping, which stays as 1 constantly. On the bottom is the final playback speed after the warping, which varies through time. This graph shows the time warping curve. We use Bezier curve to interpolate the dots. The left tangents at each dot were also adjusted so that the motion could accelerate a little bit before each dot, resulting in an enhanced beat. This video shows the effect of animation warping. Obviously, you can see the video on the right side has a better motion that matches the music.
Hi everyone, I'm Yaru from Intel.
This section is about system optimization. Dense created system is running on Intel Xeon platform. Here's the computation timeline of the system. We find the preprocessing module takes most of the time. Other modules only takes less than 1 second. When looking into the implementation detail, the preprocessing module is for music feature extraction through LibreOsa package, which needs to be speeded up. Besides, audio motion network is influenced on CPU by Keras framework. Customer says it will be better if this part also can be accelerated. So we focus on these two parts for optimization. For the first module optimization, we analyze the workload through Intel Virtual Profiler to find where the hotspot. It shows FFT pack module takes 93% usage in the workload. It is the audio analysis based on the fast Fourier transforms algorithm, so for FFT. To improve this part, we advise customer to use Intel Math Kernel Library, so for MKL. It features highly optimized threaded and vectorized math functions that maximize performance on each Intel processor family. Here is the benchmark performance data. With MKL, it only takes 2 seconds, while without MKL acceleration, it takes more than 7 seconds. However, it still needs some workaround to make MKL effective in customers' app. First, invoke pipeline has great impact on FFT performance. When using LibreOsa API in dense created system, it can invoke different functions, which is dependent on the Python environment. If the function does not invoke MKL FFT, it will be very slow. If you invoke CPy FFT, it will invoke MKL FF library, but no better than directly invoke a NumPy FFT. Besides, NumPy FFT can also invoke Pocket FFT in PPy environment, which is also no better than MKL FFT. So, to make sure the MKL lib is directly linked, we need to use Python script to fix the link path. Second, MKL FFT is not better than Pocket FFT in customers' environment. We find in their production environments, there are massive Intel platform servers running on Kubernetes. Developers need to apply cores through it. For example, 2 cores needed in dense created system. But MKL num thread is set to the total server cores by default. As a result, the CPU usage will be like this. Totally 40 cores. Each core has 5% usage. To make sure the CPU usage is not affected by Kubernetes, we need to manually set for the MKL thread. One choice is to set the app running on the applied CPU ID. Second choice is to set MKL num threads to the applied course numbers. Then the CPU usage will be only fully used on 2 cores. We can see after this optimization, audio analysis time has 20% to 80% acceleration through MKL lib. We also optimized the network inference workload through Intel OpenVINO. Intel OpenVINO is short for Open Visual Inference and Neural Network Optimization Toolkit, which can optimize and deploy deep learning solutions on Intel platform. The light blue modules are the parts provided by OpenVINO. As long as you have the trained model, you can convert the model into IR file through Model Optimizer, then load and do inference with Inference Engine. It is powered by different hardware plugins. More specifically, in our customer's case, they run network on Intel CPU platform, which can be accelerated by MKO-DNN-lib. So we help customers to convert the model into IR file. OpenVINO is very convenient and easy for implementation. As a result, it comes out great acceleration on model loading module and the inference module. The loading time acceleration makes developers start the server much faster. The inference performance improvement also reduces the latency time from client side. With all the optimization above, we got 1,300 milliseconds reduction with 20% improvement for each response, which brings better game user experience. Finally, we are glad to say Dance Creator System is already powering NetEase games. For the first half year of 2020, our choreography system has served 975,000 of requests in backing dance tasks and 106,000 requests in choreography tasks, producing widespread user-generated contents on multi-video sites. Here's a summary. For the system, it can generate highly quality production-ready dance motions for full-length songs. Besides, our system is more flexible by using beats as the measurement for music and motion. The last but not the least, it can be fully integrated with existing workflows. For the optimization, we also find several conclusions. First, Intel MKO with rich Intel processor optimizations can accelerate the Python packages. Second, computing lightweighted neural network on CPU is a good choice for both time and cost reduction. Third, using Inference Engine of Intel OpenVINO Toolkit gets great performance improvement on CPU, all powered by oneAPI. Lastly, we want to thank all the collaborators. To learn more about FUSI Lab, follow the links provided. Thanks for the watching.